Okay, so we are back again, ready to tackle another day of related rate problems. Before we begin, let's just kind of refresh our memory with our helpful hints. Basically, whenever you know something's a related rate problem, you're going to make a picture, you're going to assign variables, we want to write an equation. Once we have our equation and it's set up and ready to go, we're going to differentiate with respect to time, and then substitute any of the known values into the derivative and solve for the required rate of change. I do want to remind you, these questions do need units. So we want to, in our answers, when we're given units, we have to include units in our answers. So with our first example, I just want to see how much we remember from yesterday. A pebble is dropped into a calm pool of water, causing ripples in the form of concentric circles. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. At what rate is the total area A of the disturbed water changing when the radius is 4 feet? Okay, so if you forgot what the word concentric means, I have a little kind of picture here. So imagine this is your pebble or your rock, whatever, and here's your circles going out. So basically, we want to know, okay, so I'm going to take away my little picture here. We want to know our radius is going out, right? Our concentric circles. We are given the outer ripple is increasing at a rate, so dr dt, 1 foot per second. At what rate is the total area, dA dt, equals, I don't know. What rate is this disturbed water changing when the radius is 4 feet? So when r equals 4. Okay, there's my pictures. Here's my assigned variables. This is what I know about the situation. Now I look and I see I have A and R. So we are going to set up the area formula for a circle. I'm going to take the derivative of this equation. So dA dt equals 2 pi r dr dt. Now that I have my derivative, I can just go ahead and pop in whatever information I have. I'm solving for dA dt. This is what we're looking to find. 2 times pi, we want this when r is 4. And when r is 4, dr dt is 1. So we're just going to plug all of the information we know. So dA dt, the rate of change with area with respect to time, is going to be 8 pi. Now remember, if you don't know how to do the units, think about this. Area is going to be feet squared, and the time is going to be seconds. Okay, so I usually, at the end, I just kind of go back and I think, what's in the numerator, how do I measure that, and the denominator. And there's your answer. Moving on to example 2. Example 2 is going to be something hopefully is similar to the things we did yesterday, and just as a good refresher. So we have a small balloon is released at a point 150 away from an observer who is on level ground. If the balloon goes straight up at a rate of 8 feet per second, how fast is the distance from the observer to the balloon increasing when the balloon is 50 feet high? Now, before you get all scared, usually if you're given a situation like this, a picture would be included. However, I have so much fun drawing the pictures that I didn't put them on the paper. So we have a small balloon is being released. So we're on the ground. We've got a balloon up here. Here's my balloon. There we go. So the balloon, right, that's the height of the balloon going up. And it's being released from a person who is standing 150 feet away. So we have this guy over here watching the balloon go up in the air. Okay. So if the balloon goes straight up now, so let's talk about, we have X, we have Y, and this piece here, I usually use S when I'm dealing with these types of equations. So the balloon is going up, this is moving, and it's going straight up at a rate of 8 feet per second, so dy dt equals 8. This is constant. That distance never changes. So this distance is going to change as well. As the balloon goes up, okay, it's going to go up at a different rate. How fast is the distance from the observer to the balloon increasing? So we're looking to find the rate of change of S. So I think we have enough information right now to set up a little equation to begin. We're dealing with a right triangle. Okay, so I have this right triangle. Whenever I'm dealing with a right triangle, it's kind of safe to assume you're going to be working with the Pythagorean theorem, okay, because these are all side lengths. If we had any angles, which we're not going to do this year, then we might be using right triangle trigonometry or SOHCAHTOA. But because we're dealing with all side lengths, we're sticking with the Pythagorean theorem. So at this point, I'm going to substitute some of my variables into my equation. A squared. A squared doesn't change, so I'm going to use the actual number. Right, my A value remains constant. Plus y squared equals S squared. Now I'm going to take the derivative of this equation. The derivative of 150 squared is just 0. 2y dy dt equals 2s ds dt. Now I'm just going to pop in the information. So I want to find this when, oh, they gave us y, I'm sorry. When the balloon is 50, so when y is 50. So we have that information. So 2 times 50 times dy dt, which is 8, equals 2 times s. Now here's where I run into my first problem. I don't know what s is, so I have to figure out what s is. And if we go back to what we talked about yesterday, this length is always going to stay at 150. We want to know what s is when y is 50. So once again, all we have to do is set up the Pythagorean theorem. And after our little calculations in your calculator, you get that, square root both sides. We know we're only concerned with the positive. So we're going to plug this in for s. I want to point out right now, you need to use that whole decimal. Okay? So when you're doing a calculus problem, unfortunately, the rounding occurs at the very, very end of the problem. And, again, this is all math. This is just stuff you're going to be doing in your calculator. So I would probably get this number and then divide by that number. And ds dt is going to equal 2.530 feet per second. Oh, I guess I should actually, I want to talk about something real quickly. So I have 2 times 50 times 8, and I'm going to divide by 2 times 158. Okay, I'm sorry about this. So here I have 2.5298. We usually round to 3 places in a calc course. So if I go out one more spot, this is going to round this up to 0, which rounds that up to 3. Okay, so sometimes you will have some tricky rounding, and I just want to make you aware of that at this point in time. And there's your final answer. Let's look at the next 2 examples. The area of a circle is increasing at a rate of 4 square inches per minute. At what rate is the radius increasing when the area is 10 square inches? All right, so this one looks nice and easy. We've got a circle. Okay. So our radius is increasing. And they give us that the area is increasing at a rate of 4 square inches. At what rate is the radius increasing? So we want dr dt. I don't know what that is. When the area is 10 square inches. Okay, so that's what we know. We're dealing with area and radius, so obviously we're going to start with the ever popular area of a circle formula. I'm going to take the derivative of this. dA dt equals 2 pi r dr dt. And I'm going to go and start to substitute my given information. dA dt is 4. 2 times pi. Now when I go to plug in r, I don't have it. This is going to happen. Okay, more often than not, you're going to have to do some work to get something to plug in. So whenever that happens, go back to the situation they gave you. They gave us that our area, right? They want to know this when the area is 10. So we know our area is pi r squared, so we set that equal to 10. And when the area is 10, that means our radius, square root both sides, is square root of radical 10 over pi. Obviously, it's plus or minus, but we only want the positive one. Okay. Now here, this is going to be a mess if I plug it up over here. This is where you kind of have to know, oh, when do I rationalize things and when do I not? In this situation, to make life easier for us to plug in, we're going to rationalize this, okay? And I'm working it through with pies because more often than not, you're going to be dealing with physical numbers, not going into your calculator all the time. So now I want to make sure that square root sign goes all the way over. My r value is the square root of 10 pi over pi, and I'm solving for dr dt. And now if you look, because we rationalize down here, that's going to cancel out nice and easy. 4 is going to equal 2 times the square root of 10 pi dr dt. And the last step would just be to divide. So dr dt is equal to, oops, forgot my 2. 2 times the square root of 10 pi, and there's really nothing else you can do with that answer. Okay, and that's going to be given to us. This is going to be inches per minute, and no worries. You can leave your answer just like that. If it happens to be a multiple choice question and you want to convert it to a fraction, that's fine. If you plug that in the calculator, you would get approximately 0.357 inches per minute, okay? So we really have to know how to do things algebraically and convert over to a decimal when we need to. Last question, and then we'll be done for the day. Water is pouring into a conical tank at a rate of 8 cubic feet per minute. If the height of the tank is 12 feet and the radius of the circular opening is 6 feet, how fast is the water level rising when the water is 4 feet deep? Okay, so we have a cone. The radius, so the height is 12 feet and the radius of the opening is 6. We want to know how fast the water level is rising and it's being poured in. So dV dt equals 8. How did I know it was volume? Cubic feet. So dV dt is 8 cubic feet per minute. How fast is the water level rising when the water is 4 feet deep? So if we're thinking about the water level rising, think about this. We've got water going up in this tank. It's going up, it's going up, it's going up. What's changing as the water moves up the tank? The height, right? So dH dt is what we're looking for when the water is 4 feet deep, so when h is 4 feet. So I'm going to go over, and I do not expect you to know this. We're going to start with our volume of a cube. Pi r squared h. This would be given to you in the problem. So we start with our volume. Now before we begin, I want you guys to see something here. We have an r and an h. So this time, If I was to take the derivative, we'd wind up getting something that looks like this using the product rule. And our issue here is we don't have any information about dr dt. So we're going to have to write this equation in terms of h before we begin. Right? The only information we have is dv dt, dh dt, and h. So we have to make the relationship involve those variables. And so how do we do that? We think way back into the beginning of the year. My cone, okay, there's a right triangle formed, okay, and at different, I'm going to get similar triangles. So I can set up the relationship r is to h as 6 is to 12. So 12r equals 6h, and we know that r equals h over 2. Okay. We're going to take this and rewrite this over here, replace r with h over 2. Then we have to simplify this guy. b equals 1/3 pi h squared over 4 times h. And then ultimately r, we're going to get 1 over 12 pi h cubed. Now I can differentiate. Okay, when I go to differentiate, I get dv dt equals 1 over 4 pi h squared dh dt. Once you have the derivative, all you have to do is pop in all the information and solve. dv dt is 8 when h is 4, and I'm solving for dh dt. So this becomes 16 pi over 4, or 4 pi. And last thing you're going to do is divide each side by 4 pi. And dh dt is 2 over pi feet per minute. Now you could change this to a decimal, but why bother? We are done with this lesson. Thank you for tuning in today.